So that was fun. Okay. I was off at PyCon 2 weekends ago, US PyCon up in Cleveland. Actually, I didn't realize I had the shirt on. Uh, I forgot how much that actually kind of you connect, and if you miss the banter with people at the beginning of the meetings, you actually have no idea who's here and if you can help out. Although if the room gets too large like ODevs, you can't really do that. Nope. So let's kind of rehash this just a little bit. For the Untitled Python user group, I got us a URL, and I'm going to use it whenever possible. So pyorl.org takes you to the meetup page. I can find anything else from there. By the way, these are all just forwarding links, all of them. Speaker sign up, speak.pyorl.org. I don't want to be the only one talking up here, and me as an organizer, I haven't really facilitated me getting out of that position in a little while, so I'm going to do so. That link, speak.pyorl.org, takes you to a Google form for talk signups. We're going to try the Indianapolis Python user group format a little bit. What they do is they try to have 3 talks every single month of varying lengths. You have a beginner's talk. They actually call it a PBJ, Python Beginner Jam, and it is a 10 to 15 minute talk on any beginner or introductory topic. So an intro to that doesn't go too terribly in depth is great for that. Or let's look the ins and outs of list comprehensions. Yeah, something that can be done pretty quickly. The scope is really small. It's a great way to get some experience presenting under your belt. The next one they call right brain talks. I've rebranded it a little bit as a skills talk. So anything that is Python related, but not necessarily programming related. Some example topics that I put on the list include testing, using PyTest, unit test, talks, continuous integration, tips for Python-specific tips for interviewing for jobs, things like that, and those can be 15 to 20 minutes. And then a main talk, which can be anywhere between 30 and 60. If you don't think you have a main talk in you or a particular topic, look at one of the other two. And hopefully get some more people talking. Let's see, live stream. We live stream everything. I just turned it on when we finished our introductions. That is on YouTube. And the great thing about YouTube live streaming is all of our past talks are available as well, so that you can go home and watch them again, watch them after the fact. And I just added this one, so it might not work just yet, but we have a code repository, or a GitHub organization, and I still need to put the Flask code from the past 2 meetings that we were working on with the Google Assistant and Alexa Skills Kit backend, but that will be there. And if anyone can suggest other things that they might want from here, I can go ahead and link those. So, moving right into it, let's talk about asynchronous Python with Asyncio. Now, the biggest problem in Python is Python is only ever allowed to be run on a single processor at any given point. When you type Python, name of program, or you type Flask, my thing, or anything that runs on top of Python, it is limited to one processor, and that is it. There are a handful of ways around it. We use pooling, either threads or multiprocessing. Granted, pretty much any multiprocessing that is or threads that are spawned by Python still live on that single processor. I've seen some hacks that try to get it out, but anything that is spawned, it might be a separate process. It's still running on the same core. So if you have four cores or more on your computer, you have 3 that can still be utilized. A good way of starting to utilize some of those cores are task queues. So if you have a lot of blocking code, you can use task queues to communicate between different processes running on the same machine. These, if the process is using Python, then it's like typing Python my main app over on one terminal, and then on another terminal you can specify run this on a separate core, and you're now using multiple cores, but you are running 2 distinct Python programs at the same time. There are a handful of libraries that you can use to interop between the 2. Celery is the most popular, and it can run on, well, it can use RabbitMQ or Redis for the handoff back and forth, the messaging queues. RQ is specifically designed for Redis. There's also Huey and Dramatic, or Dramatic. I like Teak. And the other one that's not listed up there is you can write your program in another language. We're Python people. You can write anything. If you need something to be, terribly, really using all the cores, but you don't want to write your whole application in another language, Python is great. About CPython, you can write it in C++ or C. You can use all of the C bindings available to you to run it on as many cores as you have available, and then put a Python wrapper around it. Ta-da! That's, I think, a handful of the more mathematically inclined scientific computational libraries utilize that aspect of it. But for today, we're going to talk about Asyncio. Now, Asyncio, unlike task queues, it's more like pooling. It's actually built off of thread pooling and multiprocessing. It allows you to have a very nice way to interop with those 2 without having to deal a whole lot with, I would very much like to see a sig kill being arisen from your code using Asyncio. I've gotten some really weird errors from async, but we'll look at that in a bit. So a high level overview. Asyncio provides you an event loop. Think Node, or pretty much anything that runs in a browser, anything in JavaScript. If you've tried to do anything synchronous in JavaScript, I'm sorry. That's when you have to use the callback system and all of that. But with Python, we get this, using Python with Async Io and the event loop, you can get this really interesting mix between your standard synchronous code and then going asynchronous where you want it to, expressly where you want it to. Your functions turn into coroutines. And I have like little examples of what it might look like over on the sides. So you pull an event loop. We'll look at all of this later, but asyncio.get event loop, and there's only one event loop per running instance of Python, by the way. We'll get into some of the pitfalls there, but you can run as many functions or coroutines as you need. Coroutines are functions. In order to make a function a coroutine, all you have to do is add async to the front of it. Fairly simple. We'll see how it works in practice. You also have futures and callbacks as main ways to handle things. Yeah, take a seat. Sorry. So just if you're thinking Node, you're thinking JavaScript. Hey, this function is a callback whenever this one is done. Well, you can use that in Python as well. And as far as the language built-ins that are in standard Python. You don't have to import or do anything with them. You have async, await, and yield from. Await, I think async was added in, it was either 3 or 3.3 or 3.4 is one of the, 3.4?
3.5.
3, well,
2 and 3.6 for the last one.
I,
The was 3.6.
Okay.
The keywords, you can do decorators to go back.
That's right, the coroutine decorators. Yes, async await makes everything look so much better. So that's all the code that you're going to see from this point on uses async await, so the minimum Python version is going to be 3.5. And I think actually this async 4 was added in 3.6. I think this is the only time we're going to see async 4. Well, you have yield from, which is how they did it before, and it will still work. That's the preferred way to do user input, like a input in a text terminal still. But you also have yield for, or not yield, async for, async with. I think there's also async while as well. I haven't used that one personally. But we're using built-in features. Now, one of the nice things about those built-ins is Async Io is not the only asynchronous Python library. A lot of Asyncio was modeled off of Twisted. And Twisted can also use these built-ins. So, just as an example, I'm going to look at 2 main ways of organizing an asynchronous Python program, and at least these 2 or 3 things should all be full programs from beginning to end. So first is using Asyncio as your main loop. This is going to be very similar to a Node.js setup, a Node server, where instead of writing in Python def main and you do all of your handling, maybe you have a while true in there to keep things running, and then doing if name equals main run. Instead, what we do is we grab the main event loop, and we can run something until it completes, or we can run well, in this case, it runs until it completes and then runs forever. That's the way that this particular library does it, or wants to be implemented. And the example is from WebSockets. It is, at least in the current version, it is asynchronous Python from beginning to end. You cannot use it in a non-asynchronous manner, which is a great way to start learning, and sockets are a perfect way, or a perfect use case for asynchronous functionality. This is super simple. Looking at the actual hello function here. I missed some keywords in the code formatting. Okay, so all we have to do is add async to the front of our function. We treat it like a regular function. And await is whenever we want to kind of reverse the terminology to block our execution. It's not really blocking, it's quite the opposite. But in this case, WebSocket receive, it's just going to wait there until it receives any kind of communication over the socket connection. And then it will do something, and then it will wait until it sends, and then it will continue waiting to receive more information. Simple socket server. And start server is just setting up the server. But this is a whole program, and it will, in its current form, this will just run forever until it gets an error or a keyboard interrupt. Well, we'll look at an example later, because that actually is going to be a good library or a good example to run. Another one is, and this is probably going to be a little more useful in traditional projects, but is embedding Async Io functionality into traditional synchronous and blocking code environments. So if you have a thing that just all needs to happen sequentially, but you need to make 100 web calls before you can finish, you can use Async Io to make those really fast. In this particular item, you can actually see creating a bunch of coroutines programmatically down here in our list comprehension. What was I doing here? Oh, requesting different statuses. So this bit of Python code is completely runnable from scratch, but the idea is that your loop can be called from just the one point where you need to use it, and then take advantage of it using a synchronous function. And this is actually an example of AIO HTTP, which is an asynchronous request client. It's a little more weighty than if you're used to the requests library, but requests is not async compatible. So this is a great way of doing it. And this particular example is having a synchronous function calling a series of asynchronous functions, coroutines. And in this case, we create the loop outside of this function because, again, there's only one loop per running instance of Python. If you do asyncio.getEventLoop while you are already running inside of the event loop, you're going to get an error. And if you're just starting off, it might not seem that intuitive as to, well, how then do I run more asynchronous tasks if I'm already running asynchronously? We'll look at that a little later. But the hint is this little guy right here, asyncio.gather. What this little function is doing is given a list of coroutines, so functions that we all want to run at the same time. Gather is saying, all of these coroutines, I expect them to return something, in this case, the response from the web, and then turns it into a list that, in this case, gets returned. So if we were to run get add data, it would return a list of dictionaries, or at least whatever the native Python, JSONified response is from the web service. And then you can imagine there being a lot of code before and after using that. So in the last example, sockets. Last example of sockets. This example, web requests. The perfect use case for Async Io as it currently exists is for network calls. Pretty much anything involving the network where you are waiting on third parties to get back to you, third-party services. Anything involving user input, like the text input, I think it was yield from input, or if you're doing something in Pygame where you're doing touch or click events, keyboard events, and you want to be running things in the background as well, then that would be great for this Asyncio as main loop. Where in this case we only have one asynchronous function, but if you had one that you have a setup, then you create a bunch of coroutines, one of which handles user input, you have another one that handles data updating, you have another one that handles session saving, and they're just all running at the same time. So main loop, embedded tasks, and then also a quick look at callbacks. So this is more of the JavaScript look at things. It's a little more complicated when you look at consolidate, but in this particular example, we're going to be using AIO HTTP. Pretty much, I think it's the exact same function from the previous slide, and we're doing the same coroutines. However, instead of calling that from the same function, we're instead calling a new synchronous function that is supposed to clean up afterwards and do the consolidation there. So you'll see on the bottom here, which you could think of as our main. Oh, let me get. Okay, there it goes. We create all of our coroutines like we did before. We create a task So we create a task, and we say when these tasks are done, we're going to add a callback, which is consolidate, and then run forever. In this case, we're running forever because our consolidation stops the loop, and then we exit out scot-free, which is great. Always exit out of your loops properly. It's a little, in my opinion, it's a little not quite Pythonic on how to get the actual results out of these features, but that's my own opinion. But this actually does say those fetch items return the response, and then we pull the result out of the future result. It's a little weird, but it does work. So that's more of a node-like callback. And callbacks can also be lambdas, by the way. They don't have to be existing functions. No, anything can be a lambda. So before we go into that, any questions before we start live coding? Attempting the live code. All right. So let's do a new window here. Make everything large enough.
Is Async Io standard library?
Yes, Async Io is standard library. I want to say as of 3.4, 3.3, 3.4. So to keep things pretty simple, import Async Io, and we can pull out our event loop here. I'm not going to get the... Okay, let's do this here. There we go. All right. So that is all it takes to get an event loop. There we go. That's all it takes to get an event loop. And once you pull it, you don't need to pull it anymore. If you're only going to use it as your main, then you can put it in your main. Doesn't really matter. Your loop should be at least high enough that everything that you want to run in the event loop can reach it. If that means that if you have all of your functions in the root of your file, then put loop in the root of your file. If you're only going to use the loop inside of a function that's part of a larger program and nowhere else in the program is going to use it, go ahead and put it there, and that's all you need. The problem arises when, as I said before, if you're already in the event loop and you try to get the event loop, you can't do it. So what you do instead is you pass the event loop as an argument to the functions. Pretty straightforward. We'll see an example of that, or we'll see if we can create an example of that later. But basic example. If we have a function that just sleeps for a certain amount of time, let's say in a synchronous environment, you would have done time.sleep. I know I don't have it imported right now. But calling this sleeper function, we'll have it sleep for a certain amount of time, and we're adding some print statements around it to show that it's working. And just for clarification, I'm going to put these out here for later. So that is the synchronous version. To make this a coroutine, we just add async to the front, and in this case, we have Asyncio.sleep, and because that's where we are waiting, we're getting off of the event loop, and then it will be brought back onto the event loop after it's done sleeping. We put our wait keyword in there, and we're done. So this is valid Python code. It's not going to do anything yet because we haven't told it to run anything. So we can do loop dot run until complete with our sleeper, and we'll just have it sleep for a second, and that should be it. Pull up our terminal there. Oh, and let's just double check this. Python 3.6.4. I'm a point version behind, or yeah, point version. So if we run Python, oh, I need to cd. There we go. So it's going to go to sleep, and it's done. Simple as that. It's not terribly useful because we can do that pretty easily as a synchronous program. But let's say we add, and let's see, add 2. So run until complete. The first keyword, or the first argument, has to be something that actually gathers all the things that you want to run. So many things. I'm just trying to figure out what would be the best thing to do. Let's see. No. So we can. There are 2 ways that we can do this, or the 2 most common ways, depending on what you want. There's we saw earlier there was Asyncio.gather, and there's also Asyncio.wait. Gather does a little bit of extra work for you because you use gather specifically to pull the results out, while wait, in my own use, you just use wait if you're not actually expecting any results. It's a little more efficient. But there's also this really weird thing that I'll show in a little bit between the 2. So in this case, we're not returning anything yet, so we can just do wait. This should work. Oh, it takes a list. There we go. So this, we had 2 asynchronous tasks going on at the same time. It's just a little more complicated, but if you try to do both of these at the same time, you could try doing both of these at the same time using thread pooling, or the thread pool object, or multiprocessing. But we're on our way to doing some more complicated things with async. Async.wait, we're taking a list of coroutines. We're not expecting them to do any kind of results, to return anything. So we're just waiting on both of those. Runs as a complete. After 2 seconds, the last one finishes sleeping off, and we exit out. Something that we can do with both wait and gather, I believe, is outside of this list, we can do, I think it's run until equals Asyncio dot, and okay, so there's all completed. We can do first completed, and this when this gets run, we should see sleeping 1, sleeping 2, done 1, and we should not see done 2 because the first one already exited. So we're going to get out of this loop. Or maybe it's the other one. Live debugging. Okay, let's see. No. Maybe it's not run until. Let's check the docs. And let's make things bigger. Oh, then we'll make that bigger. Let's see. No, that's not what I meant. That's what I meant. Return when. It's not run until, it's return when. And that is in wait. There we go, much better. Add this over to the end of here. Now it should work. Sleeping one, done one, and we're out. So this, first, this return when, first completed. Say in that example before where you have user interaction, you can have a whole bunch of coroutines that are just while true and they will just keep on running. But then you have one, say your event input from your user, and when they click on the escape or the quit, and then you exit out of that one coroutine, and then your whole program exits. You don't have to worry about shutting down the other ones unless they were doing some kind of database connection. One of the things with Async Io is if your coroutines require some kind of cleanup tool, then you must do that. Otherwise, you get errors and you don't get connections that properly time out. So you do have to do a little bit of work there. But it's nice to know. The default value is return when all completed. But you can also, one of the other ones right there was, instead of first completed, first exception. So just keep running until one gives an exception. That's also more or less of a default thing. So if any one of your coroutines raises an exception, it exits out of the whole program for you, like you would want it to do. So,
my question, can you, with the run until, can you wake up another task when the result is finished?
Yes.
So that it's getting data, it's getting its job done as fast as it can, but when it's got the data ready for another task, how is the run until, or the wait and have the other task wait until? How does that? How do those work?
So
There's some sort of semaphore that you can set up?
Yes, one of the things that we had up just before was in callbacks here. Just because we created our coroutines and we just put our asyncio.wait directly into our run until complete. And if we wanted to do a callback, which, hey, this coroutine is done, call this, user callback.
So it could wake up another asynchronous routine that uses that result.
Exactly.
Okay.
And so.
Is that what's being done there?
Yeah. So, in this particular bit, we start. We run all of our coroutines, or we create all of our coroutines. We create a task on our loop, and explicitly say when this set of coroutines exits, call this function to do something with the results.
Okay.
It's a little less. Actually, you know what? Now that I think of it, if this code uses asyncio.gather, it probably it probably would just pass the things to consolidate. We can explore this in a little bit. But yeah, you can create a whole series of these.
And do something and get the next result.
Yeah, this is only showing one thing here, but you can say once this callback is done, go ahead and start the task up all again.
Okay.
You can also the wait and gather functions can be called within asynchronous functions. So say you have a single coroutine that gets run at a very high level with all the other high-level coroutines. Inside that coroutine, you can gather and wait on more coroutines and then process that information and have that in a while true loop.
Good. Thank you.
Yeah, there are multiple different ways of approaching the same problem. It's just a matter of what best fits the situation or what you're most comfortable with. All right. So, well, the only difference between doing this list right here, we were just doing the coroutines in that example in the slides were just created using list comprehension, but the effect is all the same. Now, if instead we do gather, which remember expects results to be returned, so let's just return the same value that we were given. We should be able to do, say, result equals that, and to make this a little bit easier to see, let's create our coroutines right here, and we'll do all this comprehension this time.
I think you might have to expand that, though.
Yeah, that's that weird quirk between wait and gather.
Why they do that?
I don't know either. Just go with one or the other. But yeah, he is right. We do actually have to expand this. Try and just keep it at range 3. And then just to show that it's doing results, and try running that. Oh, well, let's do it with the first completed on there for a second. So this should, sleeper was never awaited. Oh, I'm trying to remember. Well, no, that's not going to work. Oh, it doesn't use return when. Okay. There we go. So actually, here's something kind of fun. Our dones all printed off with the same, or in sequential order, but they were not initialized all at the same time, or at least when they were initialized, they didn't all get to print in the order that they were created. Yay, asynchronous. But we did get our results using gather, a list of everything that the functions returned. All right. So that's fine there. Let's take a look at our WebSocket example up here. Hopefully this should all just go right in there. So, socket server. And we boot this on up. Well, let's see. I'm just going to double check that this is installed here. Yeah, it's not installed on this one. WebSockets. Okay, it doesn't look like a whole lot, but we do have a socket server running up right now. And well, actually, well, no, I didn't include a link to this in the resources. So this is pulled straight from the WebSockets documentation. It's not their base examples here. It's from their getting started, but we can use this bit of code here to do their asynchronous client. And this is more or less the same thing. The only difference is they're sending back the message exactly as is. So if we, oh, I need to make that a little bigger. WebSockets. If you haven't used Async Io before this is a great and intuitive way to get started with it. 2 thumbs up. So back to our code. We'll create a sock client. Oh. And over here, we'll run this. No, not in there either. All right. So we got a connection over here. It didn't look like it closed properly. Well, no, it looked like it closed properly. I'm not sure why I brought that up. But our little socket client here sent hello world over localhost over a socket connection. And our socket server was just waiting on this line that whole time while we were building our client. It wasn't doing anything. It wasn't on the event loop. But once it received a connection there and we stopped waiting, then it did everything on the event loop. And then waited until we got the confirmation that it was sent back, printed off our I don't think we actually got anything back now that I looked at this. Wonder if they have something else on here that I'm not thinking of. No, not that one. Well, let's actually do this. This one actually has some input on it. So a quick look at the client. Same thing, just in reverse. So we are blocking on user input, which we don't really have to, but we are. We're going to wait. We're going to send. We're going to print that we sent, and then we're going to wait until we receive a string back from our socket. And we are going to do. We're going to run this function until it completes and then exit out. If we wanted to, we could do run forever, as long as we, well, run until complete. We can put a while true inside of our async def hello, or we could just say run this thing forever. Either one would work. But if we go ahead and run, save and run this one, we are opug. There we go. So we got opug, server received hello opug, and the client got back hello opug. Pretty intuitive. That's how a socket is supposed to work. The cool thing is that other than just waiting to see if you get a response, there's minimal to no processing going on either of these two things while they are running, or while they are waiting for a response. So let's move into web requesting territory. Going back to, it's here somewhere. There we go. So to be completely honest with you guys on this one, I'm not entirely sure what the response data is going to look like on this, because I'm just requesting return the following statuses from http bin.org, which is a great testing website if you haven't used it. Let's see. There we go. So importing Async Io and our web request library, AIO HTTP. We have a function that goes to that requests a certain status code from HTTP bin, and if we get a good response back, we return the JSON response from our bin there. Let's see.
Line 16 has capital L.
That's right. Silly Google trying to make the start of my lines capitalized. All right.
Does that should get all data?
Yeah, it's supposed to be. Good catch. But yes, both of these things would have both. Yeah.
There's so much magic in there. You could have been there.
Yeah. Yeah. And actually, this really should belong up here. Now, granted, there wouldn't. Well, actually, no. Never mind. I knew what I was doing earlier. So in this case, this is pulled from the. You can embed this anywhere in your code, and it will run whether it's asynchronous or not. Just note that get all data takes in the event loop as a parameter. If get all data was the only thing that was using that loop, we could call get event loop inside of that function, but then you could not call it from anywhere else in the code, because or you could. Don't do it because you don't know what's going to be called at the same time, and it could cause an error. That's why you pass it in as a parameter. But in this case, as if we were going to do this 100 times all at the same time, we would want our event loop all the way out here, highest level. But we have a synchronous function calling a bunch of asynchronous coroutines. It's going to gather the results. And for the sake of this being more visually interesting when we run it, go ahead and print those. So let's see what this does, because I have no idea if this is actually going to work. Yay! So it worked. It didn't work, but in the way that I thought it would, which is surprising for once. So, the default functionality or characteristics of running a bunch of coroutines is that the first one that gives you an exception is going to exit out your program. It's going to exit out those coroutines. So in this case, status actually returns a it returns the status code of what you requested, but it returns an empty body. So it's attempting to decode JSON with nothing. In this case, an empty text response. So it looks nice as an example, but if we just wanted to actually use this, instead of status, I can just go over here to just return JSON for everything. And it will work. We're not actually using the input for fetch a given item, but it will work. So we run this again. We have 3 identical JSON payloads, but it did what it was supposed to, and it did them all at the same time because as long as you don't hit a critical mass of as soon as the request comes back, you're already, or as long as it doesn't take too long for the request to come back and you oversaturate your processor again, while you are waiting for the request to come back from the server, your computer is already processing what it just requested from a different coroutine. If, for the sake of being really cool, let's say we're going to hack this and we're going to make 100 simultaneous requests. Run this again. There we go. That's way faster than doing for I in range 100, go ahead and grab the same URL 100 times, or any URL 100 times. So if you're doing a lot of...
You're making additional requests while the first one's still, the server's still satisfied with that.
Exactly. It's saying, hey, I have 100 of these. As long as I keep making requests, or as long as I have the processing power, I'm going to keep making requests. But as soon as an existing coroutine gets information back, I'm going to process that, and then when it's done, if I haven't gotten a response back from those yet, send another one out, and just keep doing that until they're all done. So for anything that is, you have to wait, like web requests, sockets, anything over TCP, UDP. Database connections, anything like that. Async Io, you will get a huge boost in efficiency, as long as you need to make multiple of them at the same time. A problem that people will make and don't really notice is if you don't need to take advantage of having a bunch of simultaneous non-blocking connections, it actually is more costly to create and load and handle all of the aspects of running a coroutine if you only need to ever do one at any point in time. It will actually slow you down. It's great if you're on a web server and you know you're going to be making tons of calls all at the same time, because we're going to look at Quart pretty soon here, but say if you're on Flask, maybe you have 4 workers running in a particular environment. While all 4 workers are busy, which includes blocking for any kind of database calls that your workers are making, you have more requests piling up. But if those were asynchronous, like in Quart, you can bring in those 4 requests, but while you're also making those other, while you're making an asynchronous call out to your database, you could be handling more requests. Those workers will keep going as long as they're not monopolizing the CPU time. So asynchronous Python, great for that.
Michael, is it possible to configure to say how many workers you use? For example, I remember the thread pool executor. You can say, I use 4 or 5 workers. Possible?
It depends on how you execute it. I'm sure somewhere. Well, actually, I think with wait and gather, the way that we're doing these, you'll likely bump into other limits of your computer, because it will use as many workers as the CPU will allow it. There are other ways of doing of using Async Io or Asynchronous Python where you can use what's called an executor, and you can specify this executor has 3 threads and will only ever run 3 coroutines at the same time. It's closer to doing like use with thread pool as pool. Like,
what's the difference used between thread pool executor or use this? The same thing?
No.
Isn't so the executor is if you have synchronous code. Like this is asynchronous, right? So like if you have legacy code, you could use the thread executor to kind of throw stuff in there, and you can't really use the async, so delete. Now I think, and you'd have to double check, but I think you could do, there's some queue stuff, and I think you could limit it there. I can't remember off the top of my head, I have to look. I think there is some stuff with async that you can, have like a pool, but the executor, I believe, is synchronous.
It looked like the same, but actually not.
I know, it was kind
because the example is like the same.
Yeah.
But no.
Yeah, I think that's the difference. But we could,
So this Async Io is main loop, the image on this side. They're actually not talking about the same thing here. I actually I forgot to mention this. So this using in the image, Async Io as your main thread and having thread pool as something separate. This is actually closer to conceptually. It's like using Async Io as your main loop, where you have all of your high level things going on, but for the most intense blocking code, you can think of the thread pool as something on a task queue, something that's running elsewhere. So you can, like I said, we have multiprocessing and pooling. We have task queues. We have Async Io. We can build libraries in other languages that we can call from Python that make better use of all the cores available. No one is a panacea. You can use them all together, and it's just one example in the image here of doing so. Use Async Io for what is best for use, but then also use task queues for things that are heavily blocking. At work, I actually did something somewhat similar to that, where our front end is running asynchronous loops and making sure that data is updated. But we also needed to run things through machine learning models, which are a little more intensive and very blocking. And those would just get put in a completely different Python program. We would have a task queue going back and forth between the two. It's just, I would never think of putting a machine learning algorithm in an asynchronous environment, because it's heavily blocking, and you would lose a lot of the benefits of asynchronous Python, or async and Async Io right there. So it's design choices. I'm trying to remember where it was. Any more questions? While I don't remember where I am.
Like doing an API call for like downloading a video or something like that.
Are you requesting more than one video, or are you trying to do other things?
Well, so this project I was going to work on was going to you would upload the video from an app essentially to a cloud environment, and then we would manipulate that video and then send it back.
Mm-hmm.
Would that be a good use case for that?
If
you'd have multiple app calls going on at once simultaneously.
Yeah.
To the cloud, but I'm trying to understand. I mean, in that environment, it'd be like I have autoscaler on the cloud side of it.
Yeah.
For the processing.
I think Async Io in that particular instance might be pretty good, just because a video file is very, very large. It's going to take a long time, and while the operating system is, I think one of the things is if it's a large file download, the operating system might be smart enough to put that on its own core, and while it is doing that, the processes running Python can be unblocked to then accept a call from another thing that is going to then download a video. So it might work. It'd be worth trying. I think so. Yeah.
This is not completely related to this thing about code being heavily blocking versus code that is not, but one use case that you mentioned that I'm kind of curious about is when you're working with a library that already has its own sort of event loop built in. You mentioned Pygame, for example.
Mm-hmm.
Usually the way that works is you do while true or while not, whatever, and then you're polling for events. I'm sure Pygame's not the only library like that, so I'm just kind of wondering how async would work in that kind of environment where it almost sounds like there's two disparate event loops going on here.
The kind of sort of, yeah, is one of the reasons why I brought up Pygame before is because I've actually done just that very recently. Let's see what the URL was, it's in here. So I have a little personal project that handles user input and is also supposed to update data in the back end. And Async Io seemed to be a really good example, use case there. So just kind of zooming in on the code here. So this is the main. This is one of those examples where you do your setup and then using the event loop as the main of the function. So I have two coroutines, which is my update loop, and I have one for an event loop. I'm actually passing in the same instance of a screen so they can both act on the same information, the same object. And then just running, wait until one of them is completed, which is always going to be the user input loop. And then the two functions up here, I have the input loop, which is the main Pygame event loop. So here's the while true for event in pygame.event.get, and I handle our mouse button down, which is on a touchscreen is a touch event, and then just if it's in a button, do whatever, if the button is clicked, do whatever that button is supposed to do when it's clicked, and then sleep. And I'm actually doing await async io.sleep there, and that's all that event loop is doing. Yes, it's using the Pygame event loop, but its sole responsibility is handling user input. And then another loop up here is just saying, again, it's another while true loop, and this one will never actually exit of its own free will. Is just saying, hey, if it's been longer than a certain amount of time, go ahead and refresh the data that the screen is supposed to be showing. So this is another one. You can embed systems that already have their own event loop and just use it as, hey, I want to do this, but I also want to do these things.
Okay. That's awesome.
So, yeah. I'm never shy about showing off my own projects, as people know. I'm actually wondering if I'm sure I can replicate a bug that I came across a little while ago. So we did this, we made 100 HTTP calls in 4 seconds or so from here using the guest Wi-Fi network. It's pretty fast. If you are in production, you're doing an ETL pipeline, and you need to gather data from 10 different sources, combine it into one, which then you feed into a machine learning model or something else, or into a dashboard for the higher ups. Perfect example. And it doesn't matter how long it takes. It's just your coroutines at a low enough number will only take as long as the longest one. So if the longest one takes only 2 seconds, it's going to take 2 seconds to run all 10 of your web requests, and you've saved however many seconds. So really great for that. However, there is an upper limit to how many you can do. On my computer, I'm going to completely overdo it by requesting, how many is that? Let's make it 1 million. This is going to give a very weird error that I've never actually seen before.
Either that, it's going to make HTTP bin very angry.
It might make HTTP bin very, very angry.
But not get that far.
Well,
Is that because you run out of memory or something?
no, even weirder, even more rare these days. I don't know how long it's going to take, but it should take some amount of time. If you try to make too many web requests, you will run out of file descriptors.
Oh, sure. Is it file scripts or no? That's essentially H1.
Yep. And Yeah, well, I'm not sure it's going to do it. I'll just leave it running just in case. But you can go in and fix or increase the number of file descriptors that your OS creates, but it requires setting a config argument somewhere deep in the system and then rebooting your computer. I've never seen that error before, and I don't think I ever will again.
Is that something you can release as release file descriptors?
Yeah. The OS takes care of releasing file descriptors automatically once a web request is done. I don't think my machine is beefy enough or the network slow enough like it is at work sometimes. This happened when I tried making 25,000 simultaneous web requests using two or three embedded for loops in a list comprehension to a corporate resource that takes 8 seconds to respond. So it very quickly came up to, it ran out at 1,500 simultaneous web requests, 1,500 simultaneous file descriptors. So every time it gets every time it gets a request back and the connection closes, it releases the file descriptor. Well, there were enough open connections where the OS just said, I cannot do anything more with this. Just raise an exception. Very weird. But in most Python, you're probably not going to make 25 million simultaneous web requests. But I could be wrong. Okay. We are doing great on time. So, let's... Oh yeah, my computer... My computer is not... Well, I did a keyboard interrupt, but my computer is also spinning up quite a lot right now. Exactly. Nope. Fun thing actually. If you want to get to that that file limit even faster, I noticed this when I went there recently. But you can actually run this whole website locally using Docker. Yay! But moving on, I'm gonna get back in here. So looked at some basic things. Looked at making running things concurrently. Different coroutines, sleeping, programmatically making a bunch of coroutines via list comprehension and then running them all. Our server and client socket waiting on each other, making a bunch of web requests all at the same time. So now, let's take a look at Quart. So one of the nice things with Quart, I am a big fan of Flask. For microframeworks, we've used it quite a lot at the meetup. We did some live group coding sessions last summer, building a database-backed Flask application from scratch, which was pretty cool.
Pokemon, right?
Yeah, Pokemon. Creating Pokemon. We looked at Dockerizing Flask applications back in November, December. We did Flask for our backend for our VUIs for Google Assistant and Alexa Skills Kit. So, if you're not familiar with Flask, it's a micro web framework. But Flask is not async compatible. However, there's this wonderful library called Quart. I think it is on 0.5.0 right now, so still pretty new, but it is gaining a lot of traction as people want to use asynchronous Python and requests. and it is a drop-in replacement for Flask. So on the left-hand side, there is very basic Flask, and this is actually the requesting the JSON from HTTP bin as a basic example, and using requests. And on the right-hand side, we have the same thing using Quart and AIO HTTP. As far as the Flask Quart goes, you'll notice that the only two things that changed are, instead of from Flask, import Flask, and app equals Flask name, from Quart, import Quart, app equals Quart name. Response, JSONify, request, they're all the same. They still do Jinja 2 templating, and they also maintain a list on the documentation of Flask extensions that work as is with Quart. Not all, but a good number do. Things like Flask SQL Alchemy, Flask Marshmallow, Flask Admin, I think also does. Flask Auth does as well. Two favorites of mine that don't work, unfortunately, are Flask RESTful and Flask Cores, which are very useful. But so is Asynchronous Python. So, just for comparison, I forgot I'm still in the thing. We'll get out of that, just to show that the first one works and that they are identical. Go ahead and copy that and put that into a file over here. I think I have Flask already in this environment. And so if we do Python Flask app, and we go here, well, we're going to have not found because we actually don't have an index there, but if we do JSON, we'll get the response from HTTP bin, except it's formatted because you gave JSONify. But if we go over here into the Quart side, put that in there, and I probably will have to do a pip install for Quart on here. Let's see, yes, maybe. Oh, await.json, ha 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 ha. This is what I get for not actually running the code in my examples. Wait, response.json.
Hey, dumb question. Do you need to do a pip install for Async Io, or is that a built-in feature of the language?
Built-in as of 3.4.
Awesome.
Yeah. Yay, standard library. Okay, yeah, so I do have to go back up here. All right. So what is it? Yep, 0.5.0. And then we run our Quart app instead. Go back here and refresh. Well, it doesn't actually... I actually haven't noticed that before. It doesn't do the pretty printing. But it is the same information. Yay.
Have you done any benchmarking?
The benchmarking I've done between the two, I've done some load testing. If you are just doing things locally and you're not making a web request out that is blocking, you're not going to see that much difference. But if you are, in that case, it highly depends on what you're doing. But as long as it's not just a one-off, Quart is going to be able to accept more simultaneous connections than Flask will. So you get you get your advantages out of there, and you get even more advantages if you're doing that requesting multiple different endpoints and then bringing them all back together. So you get some advantage if, just out of the box if you're making at least one thing that is yet another call. The advantages compile if you're doing that funnel. I am wondering. Actually, let's bring up the documentation. I'd like to pull up that list of extensions that work out of the box, and if anyone has any questions about the code in here, we can go over it more or make some changes to it. So, Async Io docs, AIO HTTP, Quart, and some other things in here as well. I will add the WebSockets library documentation into the back here when I post these up. There. Quart. Flask. Well, if you guys want to see any more of this. So this is just a little bit more in-depth. But yeah, it really is, you change, if it says Flask, change it to Quart. And that will take care of most of your instances. And then just make your functions asynchronous and have them await where they need to. So in this case, render template string is now just an awaitable function because it's calling yet another asynchronous function. But other than those two things, that'll get you 90–95% of the way there. If you're doing any kind of external web calls, make sure to replace what you're using with AIO HTTP, which probably should be added into the core library. Like, request should be added into the core library. AIO HTTP should be added into the core request library, or the core library. And once you get into the asynchronous world, there's tons of just weird packages like, oh, I didn't think I would have needed to do this, but I'm glad that this package already exists. Like adding asynchronous compatibility into your testing suite, adding it into your continuous integration. If you're doing Quart with GUnicorn or Nginx, you actually have to run it on a slightly different worker. You need to either manually change it to an async specific version that the Quart library includes, or you can use a library called UV-loop. I don't actually remember what UV stands for, but it's another one of these asynchronous compatible workers that GUnicorn can take advantage of. Let's see, using Flask extensions. This is the one. So to use a Flask extension, you just have to import this little patch line, but then import Flask login. You don't have to, there's no Quart login, just use everything, use all the code exactly as it is. It will work just fine. Except for Flask cores and Flask RESTful, which are the two that I use the most. Can't all, whatever. But all of these will work. Our SQL Alchemy, our what the form, our login, mail, cryptography. It's great. So that's everything that I had for the presentation. But we don't have to be kicked out of here for 30 more minutes if we don't want to. So yeah.
Do you know if there is something similar for Django?
I don't know. We can look it up. It's because Flask is so much smaller, being a micro framework as opposed to batteries included. I'm sure it's a little bit easier to port something over. I would be surprised if someone somewhere in the world is not currently working on a way to either make Django async compatible or make an asynchronous version of it, but it would take a little longer. They did just release 2.0, or last year they released 2.0, which just now supports 3.0 or 3.x. Want to just make something cool? Want to talk?
Is there any debug capability in this Async Io? Your print statements say you debug, and you judiciously add more if it's not working?
And Logger works. I personally haven't tried using some of the debugger tools that you can find in IDEs with it. I would be surprised if it didn't work, because the parts where you are awaiting, you're awaiting on specific functions, but you would have logging all around those functions and within those functions. By the time that you are using your debugger and you want to analyze the parts of your the different parts of your code, the deepest you would likely get in putting a debugger in your own code is going to be around either calls out to a third-party library or calls out to one of the standard Python libraries. So that'd be deep enough. And the nice thing as long as you're not awaiting, all of your code is technically synchronous, or it's synchronous within the flow within that Go routine. So it should work. My guess is if you're doing an interactive debugger, it would be blocking, as a debugger is. So I see no reason why you couldn't do it. And the logging library still works. The print statements obviously still work.
You mentioned that certain things have an affinity to a particular core or a particular processor. How do you tell what? Can you do that kind of assignment, or it just happen? You just try and lay out your code so it occurs that way. Can you see where things are going?
I'm not sure. At some point, it depends on how the operating system handles it. Python itself, anything that is being run by the Python process is limited to a single core. But when you make a call to file I/O, the operating system might put that on a separate core.
You have 3 different processes running simultaneously. You can assign one to a particular core. The operating system should sort that out.
I think the operating system would sort that out. I'd be really interested in finding out a way to specify. I know that I have 4, like on a Raspberry Pi. I know I have 4 cores, and I pared this down to as minimal of an operating system as possible. I want you to run these 4 Python programs, each on their own core. I'd be interested to see how you could do that, but I don't see a reason why it couldn't exist.
Couldn't you just do like multiprocessing? Like I don't know if you can pin them to a particular core, but couldn't you just do like Python multiprocessing and stuff? Or you could even use the question earlier about the executor, right? You could do that, and then if the default is the thread pool, you could change the thread pool to the process or multiprocess. I think it's process, not thread pool, something like that. And then you could run your normal synchronous Python code in that.
Mm-hmm.
But yeah, the multiprocessing, it's similar to threading, but that's how you can spin up more Python instances, so you can run more things, simultaneously. Like you're talking about going from like IO bound, which is what you're talking about. All this is IO bound.
Yeah.
You're waiting on something else that's IO related, either disk or network or socket or whatever. And then the other problem is CPU bound, like you were talking about doing machine learning or some sort of number crunching, stuff like that. That's where this is not going to be as like applicable. So you'd have to do something else like multiprocessing.
Exactly.
All the other things you could do to work around this type of thing. But
Yeah.
yeah, multiprocessing is pretty easy to use that. There's just going to be overhead, right? But if you need to like crunch some numbers or do some stuff that's going to spin up the fans, then you could do stuff like that. And it's pretty easy to do.
Yeah.
Import multiprocessing, and there's great documentation on that.
Yeah, that's where it goes back to all of the different ways that we have to either cope or escape the one core limitation, like the one processor limitation of Python. Is each of the things are not a panacea by themselves. So a judicious combination of all of them is going to be the best way to get the most performance out of a machine. Yeah.
I've seen some languages do this and some other languages won't. The coroutines, can they communicate with each other at all, or is it just they only return data and then you parse it from there?
So they can talk to each other. I didn't mention it in here, but Async Io supports signal handling. So you can send you can have one coroutine send a sig kill in the most extreme example, and have the other tasks, the coroutines that you set as a task, listen for when a sig kill gets raised by another coroutine, do the following thing.
But there's nothing at a higher level like mailboxes or queues or
Can it accept
signals are
payload?
notoriously difficult to get right.
You know, we can try that. Let's say, imagine we have a coroutine that processes something, and let's say we just use an in-memory list in the same file as a queue.
Right.
You can have one coroutine push data into that queue, and you have another coroutine pull data out of that queue.
And the question is that going to be atomic or not? I mean, is it going to be? We should try that because there might be a potential race condition there. I don't know if the operation of putting something on the queue atomic with respect to the operation of taking off. You can be sure it gets on before the step take it off or various other combinations.
If you
Well-
use the Async Io, go ahead. There's a queue specifically for Async Io.
Oh, okay.
Yeah.
Cool.
Yeah, so you want to use that one.
Yeah,
Well, that's pretty
yeah.
much
So you can
it.
control it there. If for some reason you didn't want to import anything, I could imagine, say you have something that's putting data into the list, and when it would go put data onto the list. You have another, and you have the other one that's taking data off. You can put that in a while true loop.
So these are actually threads, I guess, in some of they could race. Whereas in the simplistic event schemes, they have like a loop, just a net loop. It's all guaranteed to be, every individual little piece is blocking. So your put on the queue cannot be interrupted by some other thread who wants to get something off the queue. But it sounds like this would, unless you had some special built-in that already needed to deal with it.
Yeah.
Which is what we do. So-
Sorry, second part of that question.
Yeah.
You were mentioning that you can send signals. Is it only like set signals, or is there something more complicated, like where you can send like payload over?
Which is like a mailbox.
Okay.
Yeah. We can look. I've only seen it done with signals, but it's in Python. We're still pulling those signals from somewhere. Sigkill is not a native Python type. It's
So
not
that's
a
an
native
OS
Python
that's
thing.
an OS
Exactly.
construct.
Like
But a
it, OS
queue
does.
between coroutines would be at the Python level.
Yeah,
Would be an
it's-
OS construct.
I'm sorry if I look like I'm not paying attention, but I've been scrolling through the documentation and trying to find information about that. What would be the function that you would use to raise that the signal, just so I can get an idea where to look? If you can think it off the top of the head.
If you look in the if you search for Async Io signal handler, it's going to be there. I know the raise and listen, I think both have signal handle somewhere in the name of the function call.
Okay.
I'm trying to remember what subsection of Async Io it might be in. Actually, signal handling might have its own section, now that I think of it. So I know it's definitely in there. I can't think of it off the top of my head.
There's also a throw and things are slightly different, like with exception handling and stuff like that. There's like the a throw or something like that. I can't remember off the top of my head, but yeah, if you want to raise an exception when you're dealing with Async Io, of course you can do your normal raise throw the exception. But if you want to actually be able to handle it, and because of the way the coroutines work, you're actually returning. It's actually returning to the coroutine. There's like another keyword for a throw and to handle it that way. it's also kind of interesting because, like in the old Python, like 2.7, the old times back, when we had back in
Good old days.
yeah,
I'm still on my Mac. Come to know what's that. So.
Yeah,
That's still today for some unfortunate people.
yeah, that's true. Sorry. They had coroutines, so it was kind of interesting because the question you were asking, they actually had a send method, right? So you could send data, and it was just any arbitrary data to other coroutines. But they've I guess changed it. Maybe it just wasn't in use that much, or I don't really know. I mean, you could still, like, if you look into like coroutines and how it works, like underneath the hood and stuff, like there's still that send method. But they've leveraged that, and it's also kind of evolved a little bit, from Python 3.3, 4, and 3.5, and then, so they've kind of been changing things a little bit. So it's interesting because there's a really good talk, if you look at like the history, when it was introduced in Python 2.7 on coroutines, but that's all changed in 3.3 and up to 3.5. So I guess they want you to kind of go more towards, like queues and other types of data structures, so you can't necessarily send data from one coroutine to another. I don't really know why that is, but I was trying to send data from one coroutine to another. That seems to not be as common to use. I don't know why.
I know that it can be extremely dangerous from it overcomplicates things because people just think it's this perfect solution for everything. It really isn't. But if you design it correctly, then it can be really powerful. But I'm imagining because a lot of people when you're not trained, or not trained, but a lot of people might just not know how to do it.
The generic problem in multiprocessing in any language is that the OS provided primitives, usually, at least the old ones with signal, were essentially unstructured. So if you want to make a monitor, a piece of code that can only be entered by one thread at a time, you had to have a semaphore, and you had to be careful about signaling the semaphore when you came in or when you left. And it was really easy to get that wrong. I remember a method I saw somewhere, it had like 3 places that you could wait in it, which is a disaster. Basically what done is you only want to ever wait one place. They layer another layer on top of that, a lot of operating systems did, and they sometimes call mailboxes, essentially, which enable you to connect to processes or threads with a queue, and you're guaranteed that if you put, you can block, if the queue is empty, you can block. If the queue is full, you can block, and you're guaranteed that access to the queue is atomic. So you put something on the queue, you don't have to worry about it, someone trying to take it off before it goes on kind of stuff. And that, a lot of operating systems provide that functionality at the OS level. And Linux may even do that, I don't recall. Well, you've got all kinds of funky things like pipes in there. But that's the basic problem is anytime you start multitask, and what looks like what this Python does, it looks like Async Io hides a lot of that stuff from you. So you don't get tangled up in semaphores and signals and that kind of stuff. But that's just a mess. It's unstructured, inherently unstructured.
No, it's good. It's minor tweak to what I was saying. So the A throw, so this is in Python 3.6. So if you're doing asynchronous generators, you have to do things slightly different. So that's a new feature. If you're trying to, return data, how can I explain this? Do you know a good way to explain asynchronous generators?
Well, if people aren't familiar with the term, a generator in Python is anything that you can treat it like a list. In Python, it's called an iterable, but it generates the next response whenever it's called, as opposed to a list that generates all possible responses and keeps them in memory. The memory part is why you would want to use a generator over a list in certain circumstances.
Sure.
But if your generator is, say, asynchronously, or is doing something asynchronously internally, you can use async for on that generator, as opposed to, say, doing for item in await, something that generates a list that you have to await on. Fairly simple.
Yeah, I mean, that's a good point, because, if you want to yield, like, if it's something that's really computational, or you don't want to, take all, memory to do stuff, you want to yield data from an asynchronous function, so that's the asynchronous generator. And that's native in 3.6. If you want it in 3.5, there's a decorator that you can do, and you have to install a package to do backwards, backporting that feature. But yeah, that's where you have to do the eighth row. So it's slightly different, but
Looks like Async Io has got basically semaphores too. There's something called lock and unlock and conditions. So you could build some kind of mailbox you want.
There's something else.
it's cool stuff.
Yeah, is Asyncio is. Oh, that I just remember what it was. So while a lot of one thing that you'll notice that you would think might be included in Async Io but isn't is asynchronous file loading or opening. It's not in Async Io. It's not in the standard library, and the reason that they cite is that many or to misquote them, many operating systems do not have a standard means of calling an asynchronous file I/O operation, so they are not including it in the standard library at this time. However, there is there is a library that I saw. I'm not sure how effective it is because I haven't used it, but I know it exists, and I think it's just called File I/O or AI. No, it's AIO files. That's what it is.
Yeah, AIO files.
That I guess if the functionality exists, it will attempt to call it. Otherwise, it will just treat it like a blocking file open.
So. Yeah, and that's the thing about blocking operations is you want to be mindful of that because it's all cooperative. You've got your event loop spinning, but if you wait too long in something you've blocked, same thing with Node.js and other type of asynchronous type programming. But you wait too long, then sockets die, things fall over the place because it's meant to be. You're not supposed to do a bunch of stuff, right? You're supposed to get in there, do the thing, don't block, and then get out.
Yeah. If you have a single coroutine that is it's blocking for a long time, it's blocking all of the other coroutines that it's supposed to be running in the event loop.
So that means things start starving out, right? If you have network connection, it'll die.
Yeah. And I also just learned recently that the timeout limit on a connection to S3 is 9,000 seconds.
That's kind of impressive.
So that's something that you would not want to do. That's not an asynchronous call you would want to make if you knew that there's even the potential that it would take 9,000 seconds. So I think it's time to start closing on up, but this has been great. And if you haven't used Async Io before and you have an IO reason to do it, I highly recommend it. And if Async Io isn't quite your cup of tea, check out the Twisted library. It's not in the standard library, but it will give you similar enough functionality, and it too can also take advantage of async await and yield from functionality that is now baked into Python. So I'll just quickly put them back up on the screen here. But our links, if you want to speak next time, I haven't checked it in the last couple of days, so I'm not sure if there's anything new in there. But if you want to speak at a future meetup, speak.pyorl.org. Talks can be as short as 10 minutes on a really basic topic. So just give it a shot, and you might find that you like speaking. So thank you guys for coming out.
Actually, is the GitHub just for a platform in order to host the materials from this, or is it? Can we clone this repo, or
our organization just has some code from previous projects that we've worked on. This should now work. There we go. So github.pyorl.org sends you to our GitHub organization. Yes, I haven't touched this in a while, and that is my fault. But I will definitely be putting a link to the slides in here. Like, I think we had presentation topics. Yeah, listed previous and presentation topics. I'll be putting a link to the slides in there. I'll be putting I'll put all the asynchronous files that we ran here into their own repository, and I'll also upload the Flask code that we did for the assistants. So that will be coming, and I'll be a little more judicious about that. But yeah, so code's here. We have our live stream, which I'm about to end. Please put in presentation topics. And
oh, can I just interject? The AO HTTP is awesome. I've used that a lot. If you want to do the same stuff and get all the delicious asynchronous stuff, you can use the AO HTTP, which also supports HTTPS.
Yep.
To do networking stuff. So that's good stuff.
Yeah, great. So I will see you guys next month.
See you.
Hey,